Okay, and there we go. We're recording. So last time we were talking about directional derivatives. Remember the big idea of directional derivatives? 2 points of view on it. It's just a special case of the chain rule. Remember that one point of view on the chain rule, a point of view on, what do gradients do? Dot product with the gradient, what does that do? So it relates input changes to output changes. Well, the directional derivative is just the specific application of that idea where your input velocity is a unit vector. Right, so it's a special case of the chain rule. Or you can also think of it as being a generalization of the idea of a partial derivative. Partial derivative means you're moving with velocity in the domain being not just a unit vector, but a standard basis vector. So we're just opening it up now to the slightly more general case of other unit vectors that don't happen to be standard basis vectors. So it's they have a lot of sort of properties and feel kind of like a partial derivative, but more general. And again, it all comes out of the chain rule. Okay, so last time we ended by talking about this interpretation of directional derivatives. You can think of them as DFDS, the rate of change of the function with respect to distance as you move in, whatever direction that is your unit vector. So rate of change of the function with respect to distance. So if you're driving along a mountain road, keeping track of your altitude, again, one of my favorite examples, I find it highly relatable, right? It's physically kind of in real life kind of relatable. If you're walking, driving, whatever along a mountain road, DFDT says, how many feet per second of altitude am I gaining? That depends on how fast you're driving. The directional derivative has nothing to do with how you're driving. The directional derivative just says, how many feet of altitude am I gaining per foot traveled? That's all about the road only, right? And so not to be confused with DFDT. Okay, we talked through last time why that works. And moving along now, let's see here. I guess I can zoom back in now. So here's another interpretation. You can think of the directional derivative as being the slope of the graph of the function. Now, first I'll say, wait a minute, isn't that what a partial derivative is? Well, yeah, true, but keep in mind, directional derivatives are a generalization of partial derivatives. So it's not surprising, really. That's really not an argument for why this shouldn't be true. That's an argument for why it should, right? So specifically, when we say slope of the graph, though, not in the direction of one variable or another variable, rather in the direction defined by, let me use better color choices, defined by whatever that unit vector is. So that unit vector in the domain points in a direction. That direction defines a vertical plane that cuts through the graph. And if you think about what happens as it cuts through the graph like that, well, there's going to be a tangent line, and that tangent line, if you think about it, that tangent line, what is its slope? Well, it's the rise over the run. The rise being how much has the function changed, and the run. Oh, let's see here, color choices. I'll use, oh my gosh, the red, fine, okay. The run being how much distance have I moved in the direction of the u vector. So when we say DFDS, I mean, just kind of take a look here. DFDS, that over that, is the slope of the graph, but DFDS, previously noted, is the directional derivative. So the directional derivative is the slope of the graph. Nice little point of view there. Everybody comfortable with that? Okay. All right. So, by the way, sometimes you're going to want to know, some question is going to ask you, hey, I've got some function and there's a story about where I am and how I'm moving, blah, blah, blah. And the punchline of the question is, what's the rate of change of the function with respect to distance? And if that happens, directional derivative is exactly what you want. Right? There are other times, perhaps, when the question says, well, let's see here, I'm looking at some graph of some function, and on this graph, I'm interested in what the slope is as I move in that direction. Okay, well, if that's the case, if you want to compute the slope of the graph, boom, directional derivative is exactly what you want. Okay, here's a couple of examples. So let's suppose I'm keeping track of temperature. For example, in this room, and I'm going to speculate it might be warmer over by the windows. Right? Or let's see, which way is the sun's not really coming in. But anyway, probably by the windows, it's closer to the warmer outside. I'm guessing it's warmer over there. It's probably colder over there by where the AC is coming in. And it's probably colder down here in a dark corner, that kind of thing. So the temperature in this room is not really constant. So suppose you are flying around in this room on some path. You're moving around in some way. Well, as you move around, the temperature is going to be changing because you're moving through a non-constant domain, or a non-constant temperature function domain, basically. So in that scenario, then, very reasonable question, how much is the temperature changing? As you follow that path, how much is the temperature changing per unit distance? Right now, if it had asked how fast is the temperature changing per unit time, then we'd have a chain rule problem. But that's not what the question's asked. Very clearly, it's asking rate of change with respect to distance. Okay, so no problem. That is one of our immediate interpretations of a directional derivative. Boom. Now, we also have a explicit formula for the directional derivative. Here it is. It's a dot product with the gradient. Right? Specifically, though, dot product of the unit vector pointing in the relevant direction with the gradient. So what it's come down to at this point is we've just got to figure out what is this unit vector that points in the direction that we're going. Well, good news. Our path is parametrized. There's a very convenient tangent vector that I can write down immediately knowing a parameterization that points in the direction I'm going. It's x prime. X prime is tangent to the curve. That's not a unit vector necessarily, but it's tangent to the curve. It's pointing in the correct direction. So all I've got to do is take that tangent vector that I get from taking a derivative of the parametric curve and divide by its magnitude, thus resulting in the unit vector pointing in that direction. So in particular, don't forget to divide by the magnitude of the velocity. And boom, we're done. Is everybody happy? Okay. All right. Here's another scenario. Now, in this question, it asks, again about temperature, but this time suppose we're moving with a different velocity. Here's our given velocity. And this time, notice it says I want to compute the rate of change with respect to time. So this is not asking for a directional derivative. This is not one of our interpretations of directional derivative. So it's tempting to say, well then phooey on directional derivatives, why would I care? And if you don't use directional derivatives, you can totally answer this question, just brute force, chain rule, dot product with the gradient, just velocity dot gradient, no problem, that works fine. There is a slight streamlining that you can take advantage of, and sometimes this is helpful. So here we go, the streamlining. The thing that we're interested in, I can make a single variable calculus argument and say, look, rate of change with respect to time is rate of change with respect to distance times rate of change of the distance with respect to time. Right? Now that's just a single variable calculus chain rule thing. Right? No big. Having done that, I can then point out, oh, hey, good deal. Better change my color though. Rate of change with respect to distance, directional derivative. Special case. The directional derivative here, this is a directional derivative in the direction of a standard basis vector. That means that not only is this a directional derivative, it's literally a partial derivative. Right? Directional derivatives, correct, let me say that backwards. All partial derivatives are directional derivatives. They're just directional derivatives along, in the direction parallel to a coordinate axis. Well, these are the world's easiest derivatives to compute, right? So connecting my original question to the world's easiest derivatives to compute is convenient. I don't have to compute, in other words, the entire gradient vector. Compute all of the partials that make up the gradient vector. Apparently, I only need just this one. Okay. Specifically, the partial in the direction of the variable that our standard basis vector points in. Okay, and then the only other aspect of the question is, it says right here, apparently I've got to worry about dsdt, that's distance per unit time, that's speed. I can see the speed right there. It's the magnitude of my velocity vector, very conveniently read off because of how that is written. And so that comes along for the ride. How we doing? Yes?
Can you re-explain why you don't use the gradient again?
Yeah, so the sort of what you might call the more immediate way to do this would be to say, I want to know the rate of change with respect to time, and gradient, let's see, what's our function called? T. Yeah, gradient dot v would be, this is sort of the chain rule approach right here, right? Now, if you were to do this, notice in order to compute this thing, that the gradient is a vector whose coordinates are all of the partial derivatives. So that's, in order to flesh out what this vector is here, I would have to compute all of those partials. And then I would notice in great frustration seconds later that I'm dot producting with a vector that has a bunch of zeros in it, and oh my gosh, most of those partials that I just spent time on, I didn't need them after all, right? And so it's just one of these situations where it's more trouble than it's worth. Yeah. How we doing? Everybody happy? There is a phenomenon where when an idea is introduced later than an earlier idea, students mistakenly think that must mean that it's that it's like a replacement, and that we should just abandon the old idea and just always use the new idea. I find myself battling this assumption a lot. If I gotta pick an order to do the ideas, and sometimes two kind of we could say equally important ideas. One comes first, the other comes later. It's not to suggest that the new idea is a replacement for the old idea. So here we have an example where there's two different ways I could solve this problem. Chain rule is an option. Directional derivative is an option. I arranged this example on purpose to be one where the directional derivative was kind of the easier method, so I rigged it up to make the directional derivative look good. But just to be fair, I want to emphasize this is not always the case. Please don't assume that whenever a question asks you for a rate, the somehow right and proper thing is always to involve directional derivatives. Very often, possibly usually, directional derivatives are not that helpful, really. So just as a generic example, here's a totally generic, I've got a velocity in the domain. I want to know how fast the function is changing with respect to time, right? Very generic kind of a question. And let's consider our options. One way I could answer this question would be to do what I did on the previous page and say this time derivative, I can make a single variable chain rule argument. That's a directional derivative. This is speed, aka the magnitude of the velocity vector. Now I'm going to have to compute this unit vector, because that's what directional derivatives require. That unit vector, let's see here. I need a vector that points in the direction of my velocity, but it's got to be unit, and so I divide the velocity by its own magnitude. And therefore I find myself needing to compute this. Fine. That's plan A. Let's look at plan B. Plan B is to write down the chain rule. Recognize that the dx dt is my velocity. So here's plan B. Now, which of these is the better calculation? I argue that in this first calculation, we have done a few unnecessary things. Apparently, I'm computing the magnitude of the velocity vector pointlessly. I don't need to compute that magnitude. I certainly don't need to compute it twice, because whatever it is, it's going to cancel. unit vectors contribute nothing to the solution of this question, right? The answer all along was going to be this dot product. And the chain rule goes right to it. And the dot product was, again, bringing in unit vectors for no immediate benefit. So I encourage you to sort of think strategically about, if you have a choice between using the chain rule and directional derivatives, ask yourself the question, why am I going to bring unit vectors in? What do I win? Where's the payoff for bringing unit vectors into it? Now, our past examples here are pretty good examples, I think. Sometimes it's useful to bring unit vectors into it because the question was phrased with not only a unit vector, but a really convenient unit vector that allows me to relate a significant part of the problem to something much easier, right? So there's a great reason to use directional derivatives here. Why am I bringing unit vectors into this one? Well, because the question asked me for something that immediately equals directional derivatives that require unit vectors. So there's a reason here too. Just, make sure to think it through and have a good reason before you accidentally compute a bunch of stuff that will just cancel and not affect your answer to your question. You get the same thing either way. You might as well just do it directly. Everybody see the issue there? Okay. All right. Okay. So, that's another thing we want to talk about. We want to talk about gradients again. Now, just a quick review. What do we know so far about gradients? They started off as a notational convenience. Started off as a shorthand. I don't like having to write down all these terms in the linear approximation formula. How about let's just capitalize on the fact that it looks like a dot product and we'll rewrite it as a dot product. So gradient showed up as purely a notational convenience. That's it. We subsequently realized that, it is also algebraically, it does what derivatives are supposed to do. All right, dot product with the gradient turns input changes into output changes. Is pretty neat, right? So we've now recognized that it has this algebraic feature of it behaves like a derivative should behave, and thus we're going to start to view it not just as a notational convenience, but as its own kind of a derivative. What I'm going to do now is show you some geometric features of the gradient vector. And this is a little surprising. You wouldn't expect this right off the bat because it's defined with, again, purely algebraic motivations. It's going to turn out it's geometrically actually pretty natural. Okay, so we're going to consider a real valued function, real valued multivariable function here. And I'm going to ask what I think is a pretty reasonable question, which is, now here's our literal picture of our multivariable function, right? And here in the domain, let's suppose that I'm sitting right here, which means the value of the function is, some value. But suppose that as I sit there, I entertain the question of, hey, which direction should I start moving? Which direction should I walk? Should I walk this way or that way, or which direction should I move? Specifically with a particular goal in mind. Now, my goal, what I want to do is ask which one of these maximizes the directional derivative. Why is that natural? Well, after all, if I'm moving in a direction, the directional derivative is the thing that tells me how fast the function is changing. So look, maybe I'm cold and I want the temperature to increase as fast as possible as I walk, for example. Does that make sense? Why are we making this a matter of unit vectors? Why don't I open it up to all possible vectors? And I'm going to point out that, look, it's a given that let's suppose that the answer ends up being, suppose the answer ends up being this vector. That's the unit vector describing the direction I should walk. I think it's a given that I should walk as fast as I can in that direction. Run, don't walk, right? So the magnitude aspect of this question is, I'm going to say, obvious. How fast should I run? If I want the thing to change as fast as possible, run as fast as you can. Right? So we're going to entertain the non-obvious part of the question, which is Not a matter of magnitude, but the matter of direction. And so directional derivative is the natural thing to talk about. Is everybody on board? Okay. So reasonable question. How do we maximize the directional derivative? Keeping in mind that the directional derivative is the rate of change of the output. Okay, well, nothing to it. Directional derivative. We have a formula. Boom. It's dot product. Dot products. We have a formula. Bam. Right? So this thing that I want to maximize, I don't have to think of it in abstract terms. The thing that I want to maximize is this expression right here. Oh, wait, it's even better than that. Check this out. All of these unit vectors, their magnitude is 1 because they're unit vectors. So that factor in this dot product formula disappears because it's 1. And so really, in fact, the thing that I want to maximize is this expression right here. Now, let's think about what that is. Magnitude of the gradient. By the way, how do I compute where's the gradient in this picture? The gradient depends on the function you're looking at, which is fixed. And it depends on the point that you're sitting at. So, in particular then, at this point that I'm at, the gradient is it's some vector, and it can't change. As I look in different directions, I'm not actually moving yet. I haven't decided which direction I'm moving yet. So I'm not moving. A is constant, and the gradient of f is just a gradient of it is what it is. It doesn't depend on which direction I'm looking. So this part here then is a great big constant. So now, again, reminder, what are we trying to do? We're trying to make this as big as possible. Therefore, we're trying to make this as big as possible. One of the factors being a constant, we want to make this cosine theta as big as possible. And that's really easy. You make cosine theta as big as possible by making it 1. That's as big as it can get. And it gets that big when theta is equal to 0. And what that means then is we need the angle. Oh, let's see here. Let me do it like this. Here's our gradient vector. We've got all these different unit vectors describing possible directions that we might go. We might go in any of these directions. We want the one whose angle away from the gradient is 0. In other words, we want the one that points in the direction of the gradient. Everybody good? It's a lovely little argument. And gives a nice answer to our question. The unit vector that we're looking for, not only do we have an answer, we have a formula. Unit vector in the direction of the gradient, bam. Nice little compact formula. So, I told you I was going to tell you stuff about the gradient vector. We ended up asking a question about directional derivatives. Why is this a statement about the gradient vector? It's a statement about the gradient vector because it's telling us a geometric interpretation of the gradient vector. The gradient vector is the answer to a natural question. The gradient vector is the vector that points in the direction that makes the function increase as fast as possible. Right? The direction of the gradient vector. That's what this answer is here. The direction, geometric feature note. The direction of the gradient vector is natural, as it's the answer to a natural question. So that's kind of cool. Second half of the observation is, okay, cool. So we've decided what direction we're going to go. I didn't mean to do that. We're going to, we know what direction we're going to go. We're going to go in the direction of the gradient. That's what makes our directional derivative as big as possible. Cool. This is as big as it can get now. So how big is it? I mean, if it's as big as it can get, you'd probably want to know how big that actually is. And, well, we have a formula for directional derivatives. I can straight up punch this up because I have a formula for what my direction, my recently decided direction vector is this u that we computed on the previous page. So that means that the directional derivative, this dot product, is just, apparently magnitude squared divided by magnitude, and magnitude squared divided by magnitude is magnitude. So, it works out really nicely. So, the maximal directional derivative is this formula. Now, again, why are we continuing to talk about directional derivatives if what we're interested in is gradients? We're trying to learn stuff about the gradient. So what we've learned here, again, is that the gradient is the answer to a natural question. The gradient is the vector whose magnitude is the maximum directional derivative. Is that cool? So, so this is what I like to call then a geometric characterization of the gradient. This is interesting because it's not how the gradient came to us. The gradient came to us algebraically, notationally even, right? But we've been relying on it as being a entirely algebraic object. And now I'm going to talk about it and describe it entirely with nothing but geometric talk. Its direction, that's a geometric feature, is the answer to a natural question. Its magnitude, also a geometric feature of the gradient, is also the answer to a natural question. So, really nice way to think about the gradient vector. The gradient vector is the vector whose direction is the direction that makes the function increases possible. We call this the direction of fastest increase. Some people like to call it the direction of steepest ascent. After all, if you're looking at a graph, increasing the function means going up, so maximizing how fast it goes up would mean steepest. Right, now, but I have a personal quibble with this term. It only makes sense if you're looking at a graph. So, tragically, this is the more common term, direction of steepest ascent. You'll hear that most of the time. Just beware. It only actually makes sense. You're only talking about steepness at all if you're looking at a graph. I actually have a significant preference for this term. I think this term is nice because no matter whether you're looking at a graph or not, whatever you're looking at, independent of the picture, the gradient is always pointing in the direction that makes the function increase the fastest. So direction of fastest increase, I think is a better term, but again, you're going to more likely hear this one more often. Okay. So the direction, one of the geometric features of the gradient, is the answer to a natural question, and the magnitude also is the answer to a natural question. It's how steep is that graph. It's how fast is that rate of change in that direction. Okay. All right, how are we doing? Is everybody on board? By the way, there's a whole category of exam questions. You'll notice this when you look back at my old exams. There's a bunch of questions that say, all right, here's a function. What direction makes the function increase the fastest? Right? And, okay, the answer is, boop, right? It's the direction that the gradient vector points. That's all you got to do is compute the gradient vector and then say, all right, answer the direction that vector points. And you could even take that vector, divide it by its magnitude, and create that unit vector that literally describes that direction. I don't have strong feelings on that question. Okay. All right. Here's question. Yeah.
So if that question comes out on the exam, you can say the direction of the gradient.
Yeah, that's right. You do have to say the direction of. Okay. If you just say gradient and then put a box around that vector, then there's more information in there that I've asked for, and it's not clear that it's a spiking the football on the 2-yard line. It's kind of a deal. It's like, well, the answer is in what you wrote, but you gave me other stuff. It makes it look like you weren't clear on it. It's a minor little gripe, but it's a kind of a -1 kind of a situation. Yeah. So just remember to say direction of. Right. Yeah. Does that make sense to everybody? Okay, here's another neat geometric interpretation of the gradient. It's hard to see this one coming. There's a very strong relationship between gradients and level sets. Really hard to see this coming until it's pointed out. Now, y'all remember level sets. Remember, level sets are where the function is equal to a constant. Whatever function you're looking at is equal to a constant. So it's some surface. By the way, it sits inside of the domain. I emphasize level sets not only are not the same as graphs, they don't even live in the same world as graphs. The graph of this function would be an n+1 dimensional space. We're not even looking at a picture of that. Right? So make sure to remember that distinction. Level sets are always in the domain. Okay. So amazingly, gradients are always perpendicular to these sets. The way to see that is actually a pretty straightforward argument. If you're looking at a level set, let's ask the question, suppose I'm at some point on that level set, what would happen if I started moving in the level set, staying in the level set? First observation, the function's not changing, right? If you're moving along the level set, which means that your velocity at that point, your position differential at that point is parallel to the level set. If you're moving with any of these velocities, the function is not changing. It's constant. You're stuck on the level set. If the function's constant, that means that the df, the change differential, has to be 0. Right? These are effectively the same statement. Does that make sense to everybody? If it's not changing, then it's not changing. Okay. All right, well, here's the next observation I can make. These differentials, I have a formula for them. This is how you compute those differentials directly. They're dot product with the gradient. So what that tells me, if I have two different formulas for the differential is equal to one thing and the other thing, well, that means that these two things have to be equal, and that means that this dot product here is 0. Now, where have we heard that phrase before? Dot product equals 0. That means orthogonal. So dot product equaling 0 is the definition of orthogonal. Yeah? Okay, so fantastic then. What this means is that, let's see here, color coding this. The gradient vector is orthogonal to all of my dx's here, all of my little dx's in purple here. These are all represent input changes. So all of those tangent vectors to the surface. The gradient's got to be perpendicular to all of those tangent vectors. And how could that be? What picture can I draw that has the gradient vector being perpendicular to all of these tangent vectors? Well, it would have to be perpendicular to the surface itself. Reasonable? Okay. Cool. Now, why would we care about this? When is this going to be useful? It comes up in various ways, different situations. The example that I'm going to give you here is one that it's a question that we already know the answer to. And for whatever it's worth, I want to point out that mathematicians like asking questions where we already know the answer. Because if I already know the answer, and if I compute it a different way, then I get confirmation that the new way that I've computed it worked. That's nice, right? I also sometimes like computing the same thing two different ways because then I get a relationship between two different things. There's lots of reasons to want to ask and answer questions that we already know the answer to, right? So this is going to be one of those times we already know the answer to this question. Not a problem. It's still a good question to ask. Okay, so let's talk about tangent planes to a graph. Again, reminder, we know how to do this. The tangent plane is just the graph of the linear approximation. The linear approximation is an explicit formula we already have. We know how to do this already. Okay. Fine, let's do it a different way though. The graph of some function f is this right here. Okay. Recall, some time ago, last week I think it was, we made the observation that every graph is a level set. Now, so all I'm going to do here is just kind of move things around a little bit, right? Effectively, I'm taking this term and just moving it to the other side of the equation. That's all I'm going to do. And I get z minus f equals 0. And cool, that gives me then explicitly a level set. There it is, equals a constant. That means level set. I have a level set now of this function called g that has that formula. So I'm reinterpreting the graph as a level set, just as we did last week, or whenever that was. So, okay, now I'm going to rephrase the question then. The original question, recall, was to find the tangent plane to a graph. Rephrase, I can just as well phrase this question as I want to find the tangent plane to this level set. And phooey on that graph business. I like level sets. We have a new tool of calculus of level sets. We know how the gradient, aka a thing of calculus, the gradient of this function will be a vector that's perpendicular to this surface, namely this level set, right? And so seeing it as a level set, that particular calculus is going to be really useful. So here we go. How do we find a tangent plane to a level set? Well, let's draw a picture. Again, we're thinking about this function right here. And the level set is going to be some surface, whatever, some surface. I want to find the tangent plane. The tangent plane is going to be something like this. The tangent plane is characterized by a vector perpendicular to that plane, and I make a simple geometric argument that if my normal vector needs to be perpendicular to the tangent plane, then the normal vector also needs to be perpendicular to the level set, because the tangent plane and the level set are parallel. Because it's a tangent plane, right? Is that satisfying? Okay, so I find myself in need of a vector perpendicular to a level set. And this question is tailor-made. Right? If you want to find something perpendicular to a level set, cool. Gradients do exactly that. Everybody see that? Nice immediate application of what we just saw. So yeah, cool. So I'm going to pick, for my normal vector, I'm just going to use the gradient. Specifically the gradient of g. The gradient of the function whose level set I'm looking at here. Very importantly, not f. Right? Gradients are perpendicular to level sets. So said differently, the gradient of the function whose level set you're looking at. So g, not f. Again, I just want to make sure everyone's comfortable with that. Does everybody follow the reasoning there? Yeah. Okay, so I got to figure out how to compute this gradient. We're going to compute the gradient by taking the partials one variable at a time. What's the x partial of this expression? Well, there's no x's in here. I don't have to worry about that. I just need to take the x partial of that thing, and the minus sign comes along for the ride, and the x partial of f is, well, that. So there's the x partial. Likewise, here's the y partial. Now, what's the z partial? Well, there's no z's in there. The z partial is just, well, the z partial of just that z, which is, of course, just 1. So, a little bit of working out partial derivatives, but there then is my formula for our normal vector. And once you've got the normal vector, then don't forget we also need to have a point on the plane, and this, that color doesn't really show up very well, does it? Let me pick a different, I'll use orange, that'll stand. There we go. Okay, I need a point on that plane. The point on the plane is the point on the graph. And if you're looking at a graph of f, then that point on the graph would look something like this. And now we've got an n, we've got an x naught, and we're in business. And everything else, I'm going to let y'all read these details. This is just a little bit of algebra, but you take the normal vector. Let's see here. Let me zoom out so we can see it. Take the normal vector that we just decided on. We dot with x minus x naught being this point that we just decided on. You dot it out, multiply, move terms around, and lo and behold, the tangent plane that I was looking for. Very familiar results. The exact same result we got previously. And so we know we got the right answer. Everybody happy? Make sure to think through all this algebra that I just glossed over, right? There's significant, significant steps there. Okay. All right. So, that's the end of our discussion of derivatives. Mostly. Let me correct myself. You may recall we skipped the section on optimization, or I think in this book they call it max and min. So that, I skipped over for a reason. It's because, long story, but, it's gonna turn out that chapter 15 is the rough part of the class. Chapter 15 is where things start to get kind of wild. Chapter 15 is what you're gonna need the most time to be able to absorb, to digest, and kind of get used to weird ideas. And unfortunately, it's the very last part of the course. Right? You'd think, why don't they just take chapter 15, take a hard part of the course, move it earlier so that you can have more time to absorb those really hard ideas, the most sort of, challenging ideas in the course. And the answer is because most of the course is actually prerequisite to those ideas. So, there's a lot of stuff that I can't move to after chapter 15. But anything that I can move to after chapter 15, I want to move to after chapter 15 so that you can get chapter 15 as soon as possible, so you can have as much time to absorb it as possible. And basically the only thing that I feel like that I can get away with is the optimization, max min stuff from chapter 13. What is it? 13.5, I want to say.
Yeah.
So, yeah, is that right? Oh, thank you. Okay.
I already did that one.
Oh, you did? Oh, whoops. Yeah. Oh, well. So we will come back to chapter 13 at the very, very, very end of the course. But for now, we're done, and we're going to move on and talk about integrals. I am also going to switch over to my Math219 notes. They cover exactly the same ideas. I kind of like the way I've written them here more recently, and so I'm going to do it this way. Okay. All right, these are my chapter 5 notes, page 1. Okay, so I'm going to start off with a kind of a sort of a multivariable integral calculation that is going to seem really basic and really natural and really fundamental. And I warn you that just like partial derivatives seemed likewise natural and fundamental, but I gave you this warning that, there's much more powerful, much more truly fundamental ideas on derivatives to come, right? We started with partial derivatives because it was an easy segue. It was familiar, and that's nice. And the book did it that way, and that's nice. But when you leave this course, I hope you won't, think to yourself, if someone were to ask you at this point what most fundamentally is a derivative, I hope you won't say partial derivative. I hope you'll say, well, it's the derivative matrix, the Jacobian matrix. It's the most general relationship between input changes and output changes, both of which could be vectors. The way we relate those, Jacobian matrix, aka derivative matrix, or if you're talking about a real valued function, gradient vector. That's really what a derivative really is. The partial derivative is it's a tool that we use to understand those things. It is not itself really the fundamental thing. So there's a very similar phenomenon going on here. I'm going to start with the easiest segue into multivariable integrals. But this is not where you should hang your hat. This is just a segue the big fundamental idea is going to be coming in a few, and well, we'll see how time goes. Maybe, possibly by the end of today's lecture, we'll see. Okay, so here we go. Flashback. Single variable calculus, Calc 2. If you have a curve, and if you rotate that curve around the x-axis to then generate a surface, and you want to compute how much volume there is in that surface. Everybody remember this question, I hope? And the big idea is to slice it up into little slices. Each one of those individual slices, I can ask how much volume there is in that individual slice, and that turns into an easy little geometry question. The volume in that slice is, I just need to know the area of this cross section. Well, that cross section's a disk. Disk has an easy formula. Pi r squared, not hard to argue that r is the value of the function, right? Again, this is all Calc 2 rehash. But area of the cross section, and then times the thickness. And that thickness, you notice, is the width of a little piece of the x-axis, and is therefore dx. So here's your formula for your little dv. That goes there. And you take an integral, boom, we computed the volume. Does that look familiar? Everybody remember that from long ago? Okay. Cool. All right, here's a related question, seemingly. Suppose I have a function here. Now, just for formality reasons, I need the function to be continuous and non-negative. And we'll come back and talk about those conditions in a few. But just for our purposes here, let's make them continuous and non-negative. I can look at the graph of that function. The graph would be some surface. And I could very reasonably ask, what is the volume under that graph, specifically sitting over a particular rectangle in the xy plane? Right? So given a function, I can talk about its graph. Given a rectangle, I can talk about the volume under that graph over the rectangle. And it's a volume question. And we think to ourselves, hey, we know how to do volume questions. You take the slices and you blah, blah, blah. So let's try to do the same thing here. Let's take this volume that we're interested in. Let's take slices like that. Understand the volume of each slice. Well, the volume of the slice is going to be something it's, kind of, everything's looking good so far here. We've got to look at a cross-sectional area. And then we've got to multiply by the thickness. And the thickness here, that thickness is going to be a little piece of the y-axis, and we can say, all right, well, that thickness, we could call that dy. It kind of feels like we're in business here. And here's the problem. The one missing element is that this area is not a barnyard variety, garden variety, geometric shape. It's not a disk like it was here. Not a disk. It's also not a triangle or a square or a rectangle or something where I can just write down the formula. So it is tempting to throw in the towel and say, we're out of business. I don't know any such formulas, and so, I guess we lose. Right? But let's press on anyway. Really nice point of view on this. If I can get this to, I was hoping to... okay, well, anyway, close enough. This area that I'm interested in, that's the area under a curve, isn't it? Right? And if you think about it, this curve that I'm computing the area under, that curve is part of this graph. The heights that I need to multiply by the widths are just the value of the function. So area under a curve where I know the formula that gives me the height of that curve. We do know how to compute those areas, right? The only little asterisk, the only little detail is that the height, we see it as being the value of this function of two variables. We just have to recognize that for what I'm interested in here, y isn't changing. Y is a constant. So this is actually a function of a single input variable, x. X is going to go from A to B. Y is constant. The area that I need here to compute that area is in fact for a single explicit fixed value of y. So we treat y as a constant. And no big. This works out great. And again, a lot of this is already written down over here. But y is fixed, so that means that that's a constant. We're going to let x go from A to B, because that's what takes me then along this base like that. The height here that I'm multiplying by my dx's, that height is the value of f. And therefore this area, let's see, oh gosh, I guess I'll use orange for my area here. This area that I need is just that right there. And do keep in mind, we are computing that area for a given value of y. Now, yes, we will get a different answer for different values of y, but for any given, we can only talk about this area if we momentarily at least settle on a value of y. Settling on a value of y gives me a cross-section for which I can do this area calculation. Is everybody good? All right. So, cool. And everything after that is old news. Let's see here. Let me erase a bunch of stuff here. We just talked about how to compute this area. That's this formula right there. We're going to multiply that area times thickness. The thickness that we multiply by is a width on the y-axis, so that width is dy. That means that this area times thickness is my little piece of volume, and I add up all those pieces of volume as y goes from C to D. You buy it? Cool. We just did a kind of a multivariable calculus computation. This expression right here is going to be important. It's name-worthy. It's important enough we need to be able to refer to it. The most common term is iterated integral. I have my little micro quibble with this term. To me, iteration means you're applying the same process over and over again. I guess, motivation there for this term iterated is that we're taking an integral of an integral. And okay, I get that seems like an iteration, but very importantly, though, to me, really importantly, this inside integral is an integral that goes in the x direction. The outside integral is an integral that goes in the y direction. I don't think those are the same thing. I feel like this is, I'm on a tangent here. I think this is an abuse of the term iterated. It rubs my fur backwards just that little bit. I was so annoyed by this at some point that I tried to popularize an alternative term. I would rather call these nested integrals because, like Russian nesting dolls. Because it's one inside of the other, this much is clear, right? And it didn't catch on, and I think 20 years is enough time. I'm officially bailing on that attempt. But anyway, I would love to know if y'all ever hear anyone talk about nested integrals other than me, because I might just take credit for it. I don't think it's going to happen. Anyway, iterated integral. Very useful, allows us to compute this volume under a graph of a multivariable function, and feels like we're doing some multivariable calculus. Yeah? Let's see an example. Let's get our hands dirty. You know what? I'm sorry, I've jumped the gun a little bit. Yeah, a little bit of terminology that you do have to be careful with. The very first thing we wrote down here was this integral, right? The dy integral was the first integral that we wrote down. We argued that the volume is an integral of cross-sectional area. But when you have this expression written down and you start computing, the first integral that you compute is the dx integral, because you have to, because you need to know what that is, because it's your integrand for your dy integral. We can't start off with the dy integral. You don't even know what its integrand is yet. So you have to compute the dx integral first. So which of these two integrals is the first? Is it the blue one or is it the green one? Which one is first? I propose that the terminology is going to be confusing no matter what, because you'd either have to clarify first in the sense of the slicing process or first in the sense of the computational process, or you'd be flipping a coin, fingers crossed, hoping that the person you're talking to interprets it the way you intended. So I point out that that's just confusing. What is not confusing is that the dy one is on the outside, the dx one is on the inside. Very simple solution to that. We just sidestep the issue entirely. Let's not even use terminology like first and second. It's not particularly helpful. Inside, outside. Boom. Unambiguous. Perfectly crisp. Very convenient. So that's what I encourage. Everybody see the little micro issue? I know it's a micro issue, but still. Okay. Second thing to keep in mind, and this is easy to lose track of, but it's right here in the picture that we've drawn. While you are looking at this inside integral, right? Remember, I'm going to call that the inside. What is that inside integral? That inside integral, after all, is this cross-sectional area. And for that computation of the cross-sectional area, remember, very importantly, we're computing one cross-sectional area at a time. As I compute one of those cross-sectional areas, y is not allowed to change. It better not. I need that to stay put so I can compute its cross-sectional area there. So what that means then, let's see here, let me zoom out so we can fit this all in. This outside variable, the outside variable is the one that's fixed. The outside variable is to be treated as a constant. Right? Now that's an easy thing to forget, but you'd better remember it, because when you start computing this inside integral, you're going to be taking x antiderivatives. Every time you see an x, you know you've got to apply certain rules for how to do antiderivatives. But what on earth should I do with these y's here? Right? Answer, you treat them as constants, which is about the best answer we could have gotten. Frankly, right? It's pretty convenient. They call this a partial integral, because one variable is a variable, the other variable is a constant. So, natural terminology. Okay, now let's get our hands dirty. The question here, let's find the volume under the graph. So we're going to try to compute this volume. The graph in particular is of a given function. That's what we're computing the volume under. Sitting over this rectangle right here. And so this is a question that is exactly right down the pipe what we just figured out how to do. Right? So we're going to compute this volume. We're going to use the formula we just derived. I am going to hit the pause button real quick here and talk about this notation. This notation is very common. It's very convenient. And I just want to make sure everybody knows what it is. When you see an interval and then a times, little cross, and then another interval, that is not a cross product. This is just a different notation where the first interval is telling you what the shadow on the x-axis looks like. The second interval is telling you what the shadow on the y-axis looks like. And given those, it's clear that the only rectangle that has those shadows, and therefore the rectangle I'm referring to here, is what I have here in orange. Is that cool? It's just notation. Very convenient. Okay. Cool. All right. So let's do it. From the top half of this page, that's how you do it. Boom. Right. So we've got the y integral on the outside. And for each of those values of y, we're going to compute this x integral, giving us the cross-sectional area. The function whose graph I'm looking at is the integrand. I'm just copying straight from what we had here. Get rid of my markings here. Just volume is that formula. Yeah? Okay. So let's compute. Remember, we have to compute inside out. We have to start, therefore, with this integral right here. Don't forget, really easy to forget. Don't forget y, the variable on the outside, is to be treated as a constant. That means that this y squared right here, constant. Really easy to lose track of that. But noted as such, and now I'm going to zoom so I can focus in a little bit better. How do I take the y antiderivative? Oh, I'm sorry. The x antiderivative of x squared, 1/3 x cubed. How do I take the x antiderivative of y squared? This is where a lot of students will mess it up. A lot of students see a variable looking thing squared and they hear the word antiderivative and they think, okay, well, I guess that would be 1/3 y cubed. You can see the temptation, right? Absolutely not right. Completely wrong. Very importantly, y is a constant. That means we treat it as a constant, and the antiderivative of a constant is constant times whatever your variable is, and in this case, your variable is x. So the antiderivative of y squared is x y squared. Everybody good? Heads up, right? You're in charge of making sure that you remember how to treat each of the variables at which point in this integration process. Okay, the second little landmine that I like to point out is kind of a computational thing. We know that once you find the antiderivative, that you've got to take these bounds here, and those are the values that you plug into that antiderivative. Fine, so we know that we'll be plugging that in there, and then here's the mistake that a lot of people make. A lot of people think, hey, look at me plugging in numbers, right? I'm plugging in numbers for my variables. And a lot of students will inadvertently, absent-mindedly plug in those values for y also. Easy mistake to make. Because again, it looks like a variable and you just kind of feel like you're plugging stuff in. But make sure you don't do that. Remember, y continues to be a constant, right? As long as we're still working on the x integral, y is a constant. It stays constant. You can't plug in for constants. They're constants, right? They just stay there. Everybody see the easy oops? Now, I personally, I have a scatterbrain aspect to the way my head works, and I don't trust myself to remember to do this correctly. So I like to remind myself. I find it very helpful. My little reminder is to actually write, instead of just copying the numbers 0 and 1, I like to explicitly denote x is 0 and x is 1. I like to put that on the page as my little reminder. Plug these numbers in for x. I don't know. I find it helpful to me. Everybody's different. This is not required, but I think it'll cost you about an average of 1.5 seconds every time you work out one of these integrals. I think it'll pay off. I think it's 1.5 seconds well invested. So I encourage you to do this, yes.
Could we flip the dy and dx?
That's a great question. I'm going to come to that in a few minutes. Yeah, very good question, but let me pause on that. I'll get to it in a couple. Okay, so plug in these numbers. when you plug in the value x equals 1, that gives you this, right? Notice the y squared stays. When you plug in x equals 0 into there, you get this. And so all together then, your inside integral has worked out to that function of y. Now, it's tempting again to say, wait a minute, when you evaluate an integral, you're supposed to get a value, not a function. Okay, sure, but remember, y is a constant. And so, in fact, this is a great big, as far as the inside integral is concerned, this is a great big constant. So we have fully evaluated that inside integral. Okay. All right, now we're going to consider the outside integral. The outside integral is now doable because I can see what its integrand is. And of course, for the purposes of the outside integral, I guess I'll zoom back out. For the purposes of the outside integral, y is no longer a constant. Now we're imagining what happens with these cross-sectional areas as y varies from C to D. So y is now changed to being a variable for the outside integral as well, of course, it better be. So now we play y antiderivative games, and that goes like that. The antiderivative of y squared, because we're doing a y antiderivative, the antiderivative of y squared is now 1/3 y cubed. Note the contrast to when you were doing an x antiderivative. It wasn't. Different roles. Is everybody okay with all that? Okay. All right. And it's all plug and chug from here. This is straight up single variable calculus. Y'all can do that. Okay. All right. Moving along. So to your question, what happens if I switch the order of the differentials, or can I switch what would it mean to switch the order of the differentials? How would I justify thinking about switching the order of the differentials? The answer is that you can think of this as a computation of the exact same volume just by slicing in the other order. So let me go back to the picture up here. Here we go. Instead of taking our volume here, instead of taking that volume and slicing perpendicular to the y-axis, I am instead going to take that volume, I say you are going to take that volume and slice perpendicular to the x-axis. So you get a picture that looks kind of like this right here. You'll be interested in computing this cross-sectional area, where now it's x that is constant as you compute that cross-sectional area, and it is y that is going from C to D as you compute that cross-sectional area. So basically what we have here is we have a whole rehash of the previous calculation that we've already done that has to be done all over with the variables playing opposite roles. And I think this is a fantastic exercise to leave for y'all to do on your own. Again, you're just going to use what we've already got here in the notes as the guide, but the pictures are different. It's a very healthy exercise to think through for yourselves. Wait a minute, how is the picture different? And where is my dx and where is my dy? And which variable is playing what role at what stage? Right? And you think that through on your own, and the answer will be that you get this right here. And now there's a happy coincidence here, and that is that if you look at this answer, compare it to the answer we originally had, which is right here, notice that the dy integral that had been on the outside is now just on the inside. Huh, weird. How about that? And then the dx integral that had been on the inside, well, it's on the outside now. It looks like all we did was this. right? And notice we're changing both the order of the differentials, and we're also changing, likewise, the bounds. Unavoidably, the x bounds are from A to B, no matter how you slice it. Pun halfway intended there. A to B for x, because, let's look at the picture. It is x that is going from A to B. That can't change. That's not changing. Right? So, so happy answer. Yes, you can change the order, but the reason why is because it just happens to be that this is how the answer works out when you do that parallel computation, that analogous computation. Does that make sense? Yeah, cool. Okay, now I do warn you about one thing, though. It's very tempting to get sort of excited about this idea of hey, you can just switch the differentials and switch the bounds accordingly, and cool, no problem. Be advised, this only works when your domain is a rectangle. Now, that's the only domains we've entertained to this point, right? But it will not always be. We're going to consider non-rectangular domains. And when we have non-rectangular domains, this doesn't work anymore. Okay. All right. Okay. Now here's a temptation that's going to fail. Here's some bad news. Let me just remind you, when we were doing single variable calculus, the very first computation that everybody does in single variable calculus is to compute the area under a graph, and you get an integral, and that exact same integral works perfectly for computing all sorts of other things. How much mass is on this one-dimensional rod, or how much work does it take to accomplish a certain task. Huge numbers of applications, all the exact same integral works perfectly. So it's tempting to think, hey, now I know how to compute the volume under a graph of a function of two variables. Here's a question about mass given a density. In single variable calculus, you could just say, fine, just kind of replace your integrand with density, and the same exact expression works. Very tempting to think this, and it's wrong. And I'm sorry, it's sad that this is wrong, but it is wrong. And let me try to explain why this is wrong. In this calculation here, unavoidably critical part of the calculation is what happened right here, where I took the value of the function and I multiplied by dx and interpret that as, well, it's a height times a length, and that's an area. So very importantly, this thing in here was an area. Now, who cares? What does that have to do with anything? Well, area is something I understand. And when I'm computing area, I have great intuition for how area works. For example, if I have this area, and I ask, well, what's the area that I get when I put them together? Well, it's this area plus that area. The whole is the sum of the parts. Area has this feature that I like to call accumulation, which is just a single word describing the whole is the sum of the parts. Or said differently, area is something that if you chop it up into little pieces, you can compute on each of the little pieces and then add up the results for those little pieces. That's what I like to call the chop it up, add it up strategy, which is basically what we're doing with integrals. Okay, and I get to do that because I understand area. Now, let's ask, at that same stage, if I were doing a calculation here where I use density as my integrand, what now does this mean? And can I make an analogous argument? Well, let's see here. What have I here? This density, I'm adding up over an area, so that density is mass per unit area. And I'm going to multiply that, it seems, times dx, apparently, which is a length. And now let's ask the question, what is this deal what do I get when I multiply mass per unit area times length? And the sad answer to that question is, I don't know, that's not really a thing. That's not what you were intended to do with mass per unit area. Mass per unit area is supposed to be something you multiply times area. Right? Now, you could take a units point of view on this and argue that, just from a units point of view, I guess maybe the answer is mass per unit width. What's that? I don't know what that is. The mass isn't distributed across widths. The mass is distributed across areas. I don't even know what mass per unit width is. So, bad news. I don't know what that is. And more to the point, I don't know that this thing has this key feature that it accumulates. Can I really say that the whole is the sum of the parts here? I don't even know what that is. Right? So, I'm going to say this argument has crashed and burned. Right? Now, it works just fine for computing volumes under graphs, and kinda that's it. So, bad news, it just didn't work out the way we were hoping, and so we're kind of dead in the water. What we really need, and this is one of the reasons why I'm just, as much as I do appreciate iterated integrals, and yes, they are nice, and they are going to play a critical role in what we're going to be doing here, but they're very limited. Iterated integrals, it allows you to compute volumes, that's it. Right? I can't directly relate this construction to a computing mass or computing work or computing population or anything like that. We're going to have to find another way to answer applied questions. And real quick, the answer is going to be something called double integrals. We'll get to that next time. This is a pretty good place to draw the line. Y'all have a good day. See you later.